We're back to our notes for systems of equations. Now, in your notes, there's word problems, but I really thought this example that I use in Algebra 1 is good to explain all three situations: when we have an intersection, when we don't have an intersection, and when they're the same. So this word problem says, in order for Jose and Marty to compete each other during a wrestling season, they have to be in the same weight category. So it says Jose weighs 180 pounds and plans to gain 2 pounds per week, and Marty weighs 249 and plans to lose 1 pound per week. In how many weeks will they be the same? It says write a system, and then part B asks you to use elimination or substitution or graphing. So if we have an equation, Jose weighed 180 and he gained 2 pounds per week. Okay. It says Marty weighs 249 and loses 1 pound per week. When will they be the same? Well, if y equals this and y equals this, I want to know when this will equal this. That's a system. We just normally didn't call it that when we were doing things like that with linear equations. So if we bring one number to the one side and then bring the other number to the other side, subtract 180, you're going to get W equals 23. In 23 weeks, they'll be the same weight. It says in part C, how much will they weigh? Well, if I substitute 23 in, 23 times 2, it should be either one. It would work because they're going to be the same weight. If I substitute 23 in, that's 46. 46 plus 180, that's going to be 226 pounds. So we have two wrestlers, one starting at one weight, one starting at another. So one's starting here, one's starting here. One's losing 1 pound per week, and one's gaining 2 pounds per week. When will they be the same? So that gives you a clearer picture of when two situations would come together. Part D, though, says, what if Marty and Jose wanted to gain 1 pound a week from their original weights instead? When would they weigh the same? So say we have one guy at 249 and one guy at 180. Say they're both getting 1 pound per week. When will they ever weigh the same? Well, they won't. If they're both gaining the same constant rate of change, they're never going to intersect. So that's a word problem to kind of understand situations and when they're going to come together, when they're not. And here's the thing. These are kind of dinky equations. More complicated equations are going to happen with higher mathematics. And we'll talk about our Mathematician of the Month for October. It's about 3 ladies who use equations to actually be able to solve and find distance in real life. So we'll talk about equations then in real life. It says in number 8 and 9 and 10, here are some examples of word problems. It says the admission fee at a small fair is $1.50 for children and $4 for adults. So it's $1.50 for a child and $4 for adults. So I pretty much just go through and each sentence just translate. On a certain day, 2,200 people enter. So 2,200 people enter. And then 5,050 is the money that's collected. How many children, how many adults? So there always tends to be in these equations an amount and a money or a data or so some kind of rate of change. So we have $1.50 per child plus $4 for an adult. That's a total of money plus money equals money. And this is a total amount of people. So how many children, how many adults? A lot of students don't realize it's just simply a C and an A because it's so simple. So usually an amount is just the variable. Then you solve the system by either multiplying by -150 or setting C equal to 2,200 minus A, and you solve. Okay, here it says to raise money, and then, this is just review. I'm just going to help you set up these problems, and then you're going to finish them. It says to raise money for new uniforms, the band booster sells t-shirts and hats. The cost and sale price for each item is shown. The boosters spend a total of $2,000, so total is equals on shirts and hats. They sell for $3,375. So they had to purchase a $6 t-shirt and a $4 hat, and that's what they spent. And then they're going to sell 10 for a t-shirt and 7 for a hat. All you would do is solve the system. I would personally use elimination. You could make these 28, so multiply by -7 and multiply this by 4, or make this 60. It doesn't matter. Multiply by this by 10. That'd be really easy. And then multiply that by 6. Either one. Number 10, flying to Kampala. I think that's in Uganda. With a tailwind, a plane averaged 159 kilometers per hour. So we have the speed of the plane with the wind. The speed of the wind is a total of speed of 159 kilometers per hour. On the return trip, the plane only averaged 112 kilometers per hour flying into the wind. So you're taking that same speed theoretically, and you're removing the wind because it's going against you. Now, this is very theoretical. It wouldn't be this easy. But here's the thing. To get to these harder equations, as you get into upper math, you need to just learn how to set them up. So we have 1p, 1p equals 2p. The w's would cancel. And you'd equal a total speed. You'd find the speed of the plane, and then you'd plug back in and find the speed of the wind. All right, your homework is going to be these 6 problems. These 6 problems on this worksheet. And then I do have a few bookwork problems that I want you to do. I'm going to post them in the Honors Algebra 2 classwork. You can find the solutions to them in the systems classwork section. And then I can post a video going over these. So do these 6 and then the bookwork that I post in class. And there'll be, some of these might be on the quiz. Like I said, email me with questions that you still have about other things. And then make sure that you are chipping away at that review packet too.